This is Unit 2, Lesson 4. So as usual, please go find the tasks to complete for today. Look under assignments or on the Canvas homepage in the weekly calendar table, look for today's date, which is the 22nd of October. You're looking for tasks to complete for U2L4. This is Unit 2, Lesson 4. Goal today is to do a couple activities exploring drag, altitude, distance, that kind of thing, and start talking about orbit and how we can get things into orbit. But as usual, we'll start off with a little breakout room share. I'm going to ask a more complicated question this time around. It's in the chat. Question is, what's the best piece of advice you have ever been given? Now, this can be broad, like life advice, like YOLO, or it could be like more specific, like put a big keychain on your car keys so you don't lose them. So I'll give you about 20 seconds to think about it. So we're in the breakout rooms to chat. And again, don't overthink this. You can kind of think of like, what's your kind of life philosophy or something like that. Again, question is, what's the best piece of advice you've ever been given? We'll come back together in 2 minutes. Rooms are open. Everybody. Next task was just to review homework. The only assignments were to work on the bottle spin flip grid if you didn't finish that in class, and I am seeing 12 responses to that. There are 14 people in the class, so if you haven't posted that yet, please do so. And you can always email me the video too if it doesn't work. Then there was the flip grid. Oh, the FET, which we worked through. Again, we used class time for that. But I think most people are feeling good there. And then the 5.9 through 5.11 reading reflection, which looking at the statistics on Canvas, answers are looking pretty good. Were there any questions or anything from that chapter reading that you had questions on or were confused by?
This isn't about the reading, but Jake said he's stuck in the waiting room.
Oh. Yeah, I know oh yeah, you're right. Shoot, sorry. That's weird. It didn't like show him coming back in. So yeah, I know he's been having poor connection. Thanks for letting me know. Sorry, Jake. Didn't see you there.
No worries.
All right. So the next thing that I want to do is building on that FET assignment that we were working through. I think that's where that question was. I want to toss in just a little bit of biology and talk about human anatomy in particular and why humans are so good at throwing. We kind of ended on this question of this big evolutionary advantage that we have. So I put together a little ed puzzle. It's step number 4 on the tasks to complete list. It's titled How Throwing Made Us Human. It's 4.5 minutes long. There's about 4 open-ended questions. So I'm going to time for 10 minutes for us to work through that. If Edpuzzle freezes or doesn't work for you, there is a link, the 3rd bullet point, to the original video on YouTube that you can refer to. I'll be here to answer questions if you have any, and I'll watch our progress. Once enough of you are done, we'll just come back together. This probably won't take 10 minutes, so go for it. And again, we can throw with pretty inordinate amount of force, considering. So how does throwing in sports differ from our ancestors threw? Well, again, our ancestors were throwing spears and rocks to hunt, which they would only need to do a few times to bring down an animal. And now if you look at like a baseball game where a pitcher is throwing in the hundreds, right? Hundreds of times a baseball. And so our ancestors were hopefully not hitting animals hundreds of times with rocks. That would be unnecessary. So we see a lot of injuries now, especially in professional athletes who are totally overusing and abusing their throwing muscles. Baseball pitchers in particular, but football quarterbacks and stuff too sometimes have problems. And the different projectiles, I kind of got at that already, but spears and javelins were kind of the big thing. And one of the biggest tools that they found and what really kind of gave us a leg up in tool use is this kind of like, it looks like those things that you play fetch with a dog. It's a longer stick, but instead of putting a ball at the end, you put another spear locks into it and you can really launch it. It's pretty cool stuff. Any other questions or comments on that? I just think the human evolution stuff is really cool. Okay, I'm going to take just a few minutes here to review these slides from Hewitt that I put together to review the reading. Just want to make sure we're feeling good about this, so bear with me. We'll do some activities relating to these things. Just verbal confirmation, everyone's seeing altitude, range, drag, and satellites?
Yes.
Yep.
Awesome.
Yep.
All right. So who's a fan of Angry Birds? Angry Birds is all about projectile motion, right? And using a simulation basically to hit little targets. But if you think about it, if you're a programmer, they had to do quite a bit of math and time into figuring out what that would look like and how it would work. So just getting through the basics here. I think what's really cool is that if you take any two angles and launching them from the same elevation, so we're assuming that the throwing point and the landing point are the same, and assuming that there's no air drag at all, then if they add up to 90 degrees, they'll land in the same place. So 15-degree launch here and 75-degree launch there, or 60, 30. I think that's kind of a cool concept. But again, that's quite a bit of assumptions that we're making there, so it's not the most realistic thing. But it kind of comes with this idea of this parabolic flight that you have if there's no drag, and the fact that if it's going 30 meters per second on its way up, it's also going 30 meters per second on its way down. You kind of have this uniform behavior. Now, again, this is not actually what happens, right? Air drag would slow all of these things down, and that's the next thing that this chapter gets into. So the whole point is that the atmosphere is full of little air molecules, and you can sense them just by waving your hand around, right? You can feel the air around us. And projectiles moving through that collide with them, and they're going to slow things down. That's what drag is. And so it's going to decrease both the altitude, so how high up a projectile can go, and also decrease the range, how far an object can travel. All of those in reality are much shorter than they would be in an ideal no drag, no air drag situation. It does explain things like baseball too, if anyone's a baseball fan and has seen things like curveballs, which these pitchers can throw these insane things where the ball moves sideways and around as it's traveling. And it's all because if you get the ball to spin in a certain way, you can increase the amount of drag on one side while decreasing the amount of drag on another side, and that makes the ball curve as it's going. And you have this, what's called deflected wake. And again, this is what baseball pitchers, professional baseball pitchers are doing. It's all about how to hold the ball, how to release it and get a little bit of spin. And it's all because there's a drag acting on the baseball. So what if we got even faster moving projectiles? Baseball pitchers can pitch pretty quickly, but it gets kind of interesting because no matter what you do, anytime you drop a projectile or an object, in 1 second, it's going to fall just about 5 meters on Earth. That's just how it kind of works out with Earth's gravity. And so if that's the vertical velocity, then we need to think about the curvature of the Earth, right? What would happen if we were to drastically increase the horizontal velocity? And it turns out, and I'm going to assume that we're all in agreement that Earth is round here, but the roundness of Earth is for every 8,000 meters, which is 8 kilometers, the curvature of the Earth drops by about 5 meters. And so we just established that it takes 1 second for a projectile to fall 1 meter vertically. So here's a question. What would happen if you were somehow able to launch a projectile 8 kilometers per second or 8,000 meters per second going this way? My question to you, yes or no, is would it hit the ground? Yes or no? What do you think? Gotta be someone out there who can take a guess.
No.
No.
Yeah, very good. It would not hit the ground. It would continue to fall around the planet because technically the ground is receding away from it as it's traveling tangentially, sideways, right? Now again, this is all theoretical, but that's what orbit essentially is. Again, this is assuming that there's no drag, right? If there was air drag, then there would be air molecules smashing into our object. Anything moving that fast, 8,000 meters per second, is going to burn up if it was in the atmosphere. So true orbit is only possible outside of Earth's atmosphere. But you could theoretically, like this diagram shows you, hit yourself in the back of the head. Again, that's kind of a silly ideal example. So the last bit of the chapter gets at satellites, and this is what we're going to explore in more depth in our next lesson. But it turns out that in order to get things to orbit Earth, a satellite, the minimum tangential velocity needed is 8 kilometers per second, which I know doesn't sound like a lot, but that's 18,000 miles per hour. That's very, very fast. But that's how fast the space shuttles have to go, or the ISS. That's why it takes so much fuel for us to get out into space and to stay there. Now, again, we have to get at least 150 kilometers up because you have to be outside the atmosphere. If you were traveling that fast in the atmosphere, whatever object it is would burn up completely. And so we have to be above and outside the atmosphere. Earth's gravity always applies though, okay? It's not like Earth's gravity is drastically lowered once you're in space. You're still, if you were to stop moving sideways, you would fall down just like an apple falls from a tree, and we established that earlier. The point is that you have such a high tangential velocity, you're moving sideways so fast that you're falling around the planet, and we kind of hinted at that with the moon. I have a very short animation I just want to show you that relates to this. I got to share my computer screen this time though. Here we go. And there's a little bit of audio with it too, so let me just use computer audio.
Here's an easy animation showing how something like a satellite or the moon orbits Earth. At just the right trajectory and velocity, it's possible to make an object fall basically forever.
Right there you can see that's orbit. That's tangential velocity matching the curvature of the planet. So just thought that was a helpful animation to demonstrate that. Any questions or comments on that material from chapter 5? Pretty straightforward. All right, then we're gonna do a little activity. I'm gonna get you out of your chairs and you're gonna go do some throwing on your own. We're now on task number 6 in the task to complete. This is a Flipgrid activity. I've titled it, How Far Can You Throw? If you click on it, it'll take you to an assignment that has instructions. But you might notice that it's actually a quiz, not just an assignment. And that's because there are a couple questions and some data collection you need to do that relate to this. You're essentially going to be finding a pair of socks, going somewhere where you can safely throw them. Please avoid glass statues and fire sprinklers and things like that. You're going to throw one sock loose, just open by itself. The other sock you're going to ball up, right? Fold it in on itself, get it nice and compact, and throw that. Obviously, you're going to be looking at how there should be a pretty big difference in how far they travel, and you're going to collect some data on that and answer some questions. So everything's in the Flipgrid. I have a little demonstration video as well we should check out as usual, but I'll time for 15 minutes to work on this, and then we'll check in. So let me know if you need help. 15 minutes to work on this. Go for it.
Mr. Haight,
Yeah.
it's like completely like pitch black outside. Can I like do it and submit it tomorrow?
Yeah, you can do that. Or again, you might even have an indoor space. I mean, a sock isn't going to travel all that far. If you have a long hallway, you could try it there. But if not, yeah, you can do it tomorrow.